So now we're ready for the next two reactions. Let's start by identifying the parts of the original molecule that we're going to keep, the stuff that we don't need to add, all the carbons that we're coming with, and also identifying the portion of the molecule. So this is the portion of the molecule that needs to get added. And we can see that that's an acetal, so we know we need to do this acetal reaction. So let's start by working with that. We're going to work this reaction backwards. So when we're trying to do retrosynthesis of an acetal or figure out where the acetal came from, we are going to focus on the OCO. We're going to pick either one of the oxygen-carbon bonds and we're going to make it a double bond. The other oxygen-carbon bond we're going to break. So we are going to break that one right there, and we're also going to break the piece off of the carbonyl's oxygen. So let's redraw the stuff in yellow. And there's that carbonyl group. And then I'm going to draw over here. I have this guy. That's the part that I circled. To that, we need to add an OH and an H, and this is an acid-catalyzed reaction. So here we are, making good progress. And now I'm going to highlight these carbons that are being kept. We need to figure out how to convert that starting alkane to this particular molecule right here. Well, the starting alkane, back to here to this guy has no functionality on it at all. So whenever we have a molecule with no functionality, the very first step is that we need to do a free radical halogenation to put functionality on the molecule. So I just did the last step of this synthesis, and now I'm skipping to do the first step, and we're going to kind of meet in the middle. So we're going to do a free radical halogenation. I'm going to use NBS with light. And remember that this is going to selectively halogenate the most substituted carbon in the molecule, which is this carbon right here. So that means that we are going to make this guy. And you can see that we're doing pretty good. If we're looking ahead, what we're trying to do is move our functionality from this carbon to the adjacent carbon. That's not too tricky. And we're also going to change that functionality to an OH or an aldehyde, but we can totally do this. So first step, moving functionality. If we want to move the functionality from one carbon atom to another, our strategy for that is to eliminate. So we want to do an elimination, and we want to eliminate in between those the carbon that we're at and the carbon that we want to go to. So we're trying to make the least substituted alkene here. We've got some situations that will prevent any other alkene from being formed, but let's just be consistent with bulky base, least substituted, etc., just to keep things as normal as possible. And so when we do this elimination, we're going to get this alkene right here. And so now what we want to do is put our functionality out here. And we could really, just technically put anything out there and we'll be able to convert it to our aldehyde. But it would be great if we could put an oxygen out there on the end. That would just make things a little bit easier, and we can totally do that. We just need to do an anti-Markovnikov addition to this carbon-carbon double bond. Anti-Markovnikov addition of water is going to be BH3, THF, hydrogen peroxide, H2O2 in basic conditions. So that will give us this guy, this alcohol. And we can oxidize alcohols to aldehydes using PCC. A lot of times the solvent, CH2Cl2, is also added. So there we go. That was a lot of steps, but there it is. The second reaction of this set is a whole lot simpler, which is a good thing because I don't have a lot of room left. I'm going to write it up at the top. So when we're looking at the second reaction, we can see that we are forming this cyanohydrin, and that comes from a ketone or an aldehyde reacting with HCN. So I'm going to start backwards with this. I'm going to put it way up here at the top of the page. our OH and CN. This comes from HCN, and a lot of times we want to boost it with a little cyanide ion along with it. And our prior reagent was ketone in this case, so the carbon-oxygen single bond is starting as a carbon-oxygen double bond, and we're just adding the cyanide to that. Now we want to show how to form that cyclohexanone from cyclohexene. Probably a good way to do that would be to have cyclohexanol and oxidize it. Sodium dichromate, Na2, Cr2, O7, sulfuric acid, that will do that oxidation. And we can get the cyclohexanol from cyclohexene with any one of our three methods for adding water to a double bond. So you can just use acid-catalyzed hydration. And because we don't have to worry about Markovnikov or anti-Markovnikov or rearrangement or anything.